What does the word weather conjure in your mind? Perhaps it's the gentle patter of a spring shower on a window pane, or the bracing chill of the first autumn wind carrying the scent of wood smoke and decaying leaves. It might be the immense electric power of a thunderstorm, a dramatic spectacle of light and sound that reminds us of nature's fury. For us here on Earth, weather is a cycle of water. It rises from the oceans as vapour gathers into clouds of liquid droplets or ice crystals and returns to us as rain, hail or snow. This cycle is the planet's lifeblood, a process so fundamental, so deeply ingrained in our experience that we project it outwards into the cosmos. When we imagine other worlds, we instinctively search for comforting parallels. We look for blue skies, for fluffy white clouds, for the promise of the liquid water. We have been conditioned by our own existence to see the universe through a terrestrial lens, believing that the rules governing our oasis must surely apply elsewhere. But the cosmos is under no obligation to conform to our expectations. Its imagination is infinitely more vast, more violent and more creative than our own. Out there in the crushing blackness between the stars are worlds that defy every notion of what a planet should be. Worlds that force us to tear up our dictionaries and redefine the very meaning of weather. What if on one of these worlds the clouds were not made of water? What if instead they were shimmering incandescent veils of vaporized rock? What if the sky was not a placid blue but the seething, furious orange of a blast furnace? And what if the rain? What if the rain that fell from those alien clouds was not a life-giving shower, but a downpour of molten liquid iron? This is not science fiction. This is not a fever dream from the edge of astronomical theory. This is a reality unfolding right now 640 light-years from Earth. A place that is challenging everything we thought we knew about the limits of nature. Our journey to this impossible world begins as all cosmic journeys do, with a single point of light lost in the celestial tapestry. For millennia, we saw the stars as fixed, unchanging decorations on a celestial sphere. We charted their paths, named their constellations, and told stories about them all while believing we were utterly alone. Our solar system, with its familiar family of planets, seemed to be a unique and privileged creation. Then in the late 20th century, a revolution began. Our telescopes grew more powerful, our techniques more sensitive. We learned to detect the impossibly subtle signs of other worlds orbiting other suns. The first discoveries were tentative whispers in the cosmic static. A tiny, almost imperceptible wobble in a star's motion. A fleeting rhythmic dimming of its light as a hidden planet passed in front of it. These were the clues that unlocked the floodgates. Suddenly the universe was teeming with planets. Not just a few, but thousands. Tens of thousands. And with each new discovery, the neat, orderly picture of our own solar system was shattered into a million confounding pieces. We found planets larger than Jupiter, orbiting their stars in a matter of days, their atmospheres scorched to unimaginable temperatures. We found super-Earth's rocky worlds far more massive than our own, whose immense gravity might crush any prospect of life. We found rogue planets cast out from their parent systems, doomed to wander the interstellar void in perpetual darkness. The Exoplanet catalogue became a gallery of cosmic freaks, a testament to the universe's boundless capacity for the bizarre. Each one was a new puzzle, a new challenge to our theories of planetary formation. But even in this menagerie of alien worlds, some stand apart. Some are so extreme, so utterly hostile to the chemistry of life as we know it, that they seem to belong more to the realm of mythology than astronomy. One such world circles a star in the constellation Pegasus. Its official designation is WASP 76b. It is a monster. A gas giant nearly twice the physical size of our own Jupiter, yet somehow less massive. It is a puffy, bloated sphere of superheated gas, an object so distended by its star's ferocious heat that its very existence seems to defy the laws of physics. It orbits its parent star at a terrifyingly close distance, more than 10 times closer than Mercury is to our Sun. Its year, the time it takes to complete one full orbit, is less than 2 Earth days. Imagine that. A world where an entire year flashes by in just 43 hours. This extreme proximity has a profound and devastating consequence. The planet is tidally locked. Just as our moon always shows the same face to the Earth, WASP 76b is trapped in a gravitational handshake, with its star forced to present one hemisphere to its sun for all eternity. This has carved the planet into two irreconcilably different realms, two worlds in one. The dayside is hell. It is a domain of perpetual unrelenting daylight, a cosmic anvil, hammered by radiation thousands of times more intense than that which reaches Earth. Here temperatures soar to more than 400 degrees Fahrenheit or 2,400 degrees Celsius. This is not just hot. This is a temperature that dissolves the very definition of matter. It's hotter than the melting point of every known mineral on Earth, hot enough to vaporize solid iron to turn rock into gas. The dayside of WASP 76b is a planetary-scale furnace where the elements we use to construct our cities, our bridges, our machines, are boiled away into a transparent incandescent atmosphere. It's a place where the very ground beneath your feet would not melt but would simply vanish into a shimmering haze. Molecules themselves are torn apart by the sheer thermal violence. Hydrogen atoms are ripped from their chemical bonds, creating a seething soup of elemental gas under a star that never ever sets. The sky here would be a blinding, featureless glare, the air a colossal lens focusing the wrath of its sun. Now let us cross the Terminator, the line that separates eternal day from eternal night. This is not a gentle, lingering twilight like the one we know on Earth. It is a razor's edge, a zone of unimaginable chaos. Here, the staggering temperature difference between the two hemispheres drives the most violent winds ever conceived. Supersonic gales screaming across the Terminator at speeds exceeding 10,000 miles per hour. Winds so powerful they could circumnavigate our entire planet in less than 3 hours. These are not winds of air, but winds of vaporized elements carrying the boiled essence of the dayside into the relative cool of the night. And the night side is a different kind of alien. It is a realm of perpetual star-dusted darkness, forever turned away from the brutal onslaught of its sun. But cool here is a dangerously relative term. The night side of WASP 76b still simmers at a blistering 2,700 degrees Fahrenheit or 500 degrees Celsius, hot enough to melt steel, lead and aluminum with ease. It's a darkness that glows with its own immense internal heat. For years, astronomers theorized about what this incredible dichotomy would mean. They built complex computer models attempting to simulate the physics of this two-faced world. And from these simulations, an astonishing, almost unbelievable hypothesis emerged. A new kind of planetary weather cycle. The models predicted that on the ferociously hot dayside, among the many elements being vaporized into the atmosphere would be iron. Not iron oxide or rust, but pure elemental iron. The same material that forms the core of our own planet. This iron gas, invisible in the searing heat, would be swept up by those phenomenally powerful winds. It would be carried across the Terminator, a river of atomic iron flowing from the day into the night. As this superheated, iron-rich gas cloud entered the cooler but still scorching night side, the temperature would drop by almost 2,000 degrees. And at this lower temperature, the iron would no longer be able to exist as a gas. It would begin to condense. Just as water vapour in Earth's atmosphere cools and condenses to form clouds of liquid droplets, the iron vapour on WASP 76b would condense. It would form clouds, not of water but of incandescent molten iron, shimmering metallic clouds glowing faintly in the eternal twilight. And from these clouds, the models predicted it would rain. It would rain liquid iron, a relentless heavy downpour of metal falling through the thick, superheated atmosphere of the night side, returning the element to the planet's depths before the cycle begins again. It was a breathtaking idea, a vision of nature operating at an epic, almost unimaginable scale. But for years that's all it was, a theory. A brilliant inference based on the light we could gather from 640 light-years away, proving it was another matter entirely. How do you prove that it's raining iron on a world you can never visit, a world so distant that it appears as nothing more than a faint flicker against its star? You cannot send a probe. Any spacecraft we could build would be instantly vaporized by the planet's heat. You cannot take a direct picture of the clouds. The planet is too faint and too close to the blinding glare of its sun. To find the proof you need to become a cosmic detective. You need to analyze the starlight itself, looking for the chemical fingerprints left behind as it passes through the planet's atmosphere. For years, even our most powerful telescopes like the Hubble Space Telescope could only provide tantalizing hints. They could confirm the presence of certain elements, but they couldn't map their location with enough precision to prove the rain cycle. They could see the smoke, but they could not find the fire. The scientific community was left at an impasse, armed with a spectacular theory, but lacking the definitive evidence to confirm it. The mystery of the iron rain of WASP-76b remained just beyond our grasp. To bridge that gap, to make that final crucial observation, we would need a new eye on the universe. An instrument of unprecedented power and sensitivity, a machine engineered to perceive the cosmos not in the visible light we see, but in the infrared spectrum, the realm of heat and chemistry. We needed a technological leap as significant as the invention of the telescope itself. And now we have it, the James Webb Space Telescope. A marvel of human ingenuity 1,000,000 miles from Earth, its gaze shielded from the sun by a 5-layered shield the size of a tennis court. Its primary mirror, a vast honeycomb of 18 gold-plated segments, is the most perfect surface ever created by humanity. It is a time machine capable of peering back to the dawn of cosmic history. But it is also a cosmic laboratory. It can capture the faint light from a distant star after it's filtered through the atmosphere of an exoplanet like WASP-76b, and dissect that light sliver by sliver, wavelength by wavelength. Within that spectrum of light lies a code. A barcode written by the atoms and molecules in the planet's atmosphere. Each element absorbs and emits light at specific unique frequencies. By reading this code, the James Webb Space Telescope can do what was once thought impossible. It can create a chemical map of an alien world's atmosphere. It can tell us not just what is there, but where it is. It can distinguish between the chemical soup of the dayside and the condensing atmosphere of the nightside. It holds the key to finally definitively answering the question, is there truly a world where clouds of metal drift across a glowing sky, and where the storms unleash a torrent of molten iron? This is the story of that quest. The story of how scientists aimed our most powerful instrument at one of the most hostile environments in the known universe. It's a story of discovery, of technological triumph, and of the profound realization that the galaxy is filled with wonders that beggar our wildest dreams. We are about to journey to the terminator of WASP-76b to stand at the precipice between eternal day and night and witness the proof of a weather system born of fire and metal. The data is in, the evidence has been gathered, and what it reveals will reshape our understanding of planetary extremes forever. What if our home is the anomaly? What if this tidy, elegant arrangement of planets we call our solar system, with its small rocky worlds huddled close to the fire, and its grand gaseous giants dwelling in the cold distant dark, is not the grand cosmic rule but the rare exception? For millennia, humanity had only a single example of a solar system, our own, from which to build our entire understanding of creation. This one data point became the bedrock of our cosmic identity, an unspoken truth that felt as fundamental as gravity itself. It was the blueprint we expected the universe to follow. We imagined that across the uncounted starfields of the Milky Way, planetary families would echo our own. We drew pictures, wrote theories, and built elegant models, all based on this singular, comfortable assumption that solar systems are orderly places that planets form in predictable orbits and remain there for eternity. It was a beautiful, logical, and deeply reassuring story we told ourselves. A story that in the final decade of the 20th century was about to be torn apart by a ghost in the machine, a whisper from a sun-like star 50 light-years away that would forever change our place in the universe. For generations, the search for other worlds was the stuff of philosophy and fiction. Actually finding them seemed an impossible task, like trying to spot a firefly next to a lighthouse from 100 miles away. The light of a planet is utterly insignificant, a mote of dust lost in the cataclysmic glare of its parent star, so astronomers had to get creative. Yet, they realized that you don't look for the planet, you look for its betrayal. You search for the subtle rhythmic influence it exerts upon the very star it orbits, a gravitational tug-of-war played out across millions of miles. This revolutionary idea gave birth to a technique of exquisite sensitivity, a method known as radial velocity. Imagine two dancers spinning in a cosmic waltz. Even if one partner is invisible, you can still infer their presence by watching the movement of the other. As a massive planet orbits its star, its gravity doesn't just keep it in line. It pulls back, forcing the star to perform its own miniature orbit, a slight, almost imperceptible wobble. From our vantage point light years away, this stellar dance is revealed in the star's light. As the star wobbles towards us, its light waves are compressed, shifting ever so slightly towards the blue end of the spectrum. As it wobbles away, the light waves are stretched, shifting towards the red. This is the Doppler effect, the same principle that changes the pitch of a passing siren, but applied to the very fabric of light itself. By the early 1990s at the Haute-Provence Observatory in southern France, two Swiss astronomers, Michel Meyer and Didier Queloz, were masters of this art. They had built a spectrograph of unprecedented precision, an instrument capable of detecting a wobble in a star's motion as slow as a person walking. For months, they pointed their telescope at the star 51 Pegasi, a sun-like star in the constellation of the Winged Horse, patiently collecting its light night after night, searching for the telltale pulse of an unseen world. They were expecting to find a planet like our own Jupiter, a stately giant on a long looping orbit that would take a decade or more to complete. Its gravitational signature would be a slow, gentle sine wave emerging from the data over years of patient observation. But that is not what they found. Instead, the data screamed at them. A powerful, clean, and ridiculously fast signal appeared almost immediately. The star was not just wobbling, it was lurching back and forth with a period of just over 4 Earth days. The implication was so staggering, so utterly heretical, that they first assumed their instrument was broken. They checked everything, reran the numbers, and stared at the results in disbelief. The data was undeniable. There was a planet there, at a world at least half the mass of our own Jupiter, but it was clinging to its star in a blisteringly close orbit, a mere sliver of the distance between Mercury and our Sun. It was a behemoth in a place where behemoths were not supposed to exist. This discovery, the now famous 51 Pegasi b, sent a shockwave through the astronomical community. It was a cosmic monster that had no right to be there, a violation of the sacred texts of planetary formation. According to everything we understood, a gas giant is a creature of the cold. Its creation is a story written in ice. In the primordial disk of gas and dust that swirls around a young star, there exists a critical boundary known as the frost line. Inside this line, closer to the star's heat, it is too warm for volatile compounds like water, ammonia, and methane to freeze into solid ice grains. All that can clump together here are tiny specks of rock and metal, the seeds of small terrestrial worlds like Earth or Mars. But beyond the frost line, in the frigid outer reaches of the burgeoning solar system, the universe becomes a much richer construction site. Here, ice is abundant, vastly increasing the amount of solid material available. These icy particles stick together, growing into massive planetary cores 10 times the mass of Earth. Once they reach this critical size, their gravity becomes a runaway force, pulling in colossal amounts of hydrogen and helium gas from the surrounding disk, swaddling themselves in the thick atmospheres that define a gas giant. Our own Jupiter and Saturn were born this way, out in the cold, far from the sun's fire, and they have remained there for 4.5 billion years, the loyal distant guardians of our solar system. But 51 Pegasi b spat in the face of this elegant theory. It was orbiting deep inside its star's fire, a realm where it could never have accumulated the ice necessary for its birth. The initial reaction from many scientists was outright skepticism. Perhaps they argued it wasn't a planet at all. Maybe the star itself was pulsating, or perhaps the signal was the result of star spots rotating into view, mimicking the Doppler shift. Others proposed it was a brown dwarf, a failed star locked in a tight binary embrace. But as Meyer and Queloz's data held firm under intense scrutiny, and as other teams began to find more of these hot Jupiters around other stars, a radical new idea began to take hold. An idea that replaced our vision of orderly, placid solar systems with one of violent, chaotic youth. What if these giants weren't born where we found them? What if they were migrants born in the icy depths of their systems, just as our theories predicted, but then embarked on a destructive inward journey? This new theory of planetary migration proposed that through complex gravitational interactions with the primordial disk of gas and dust, from which they formed these colossal worlds, could lose orbital energy and begin a slow, calamitous death spiral toward their parent star. They would have bulldozed their way through the inner solar system, flinging any smaller Earth-like planets into the star or out into the lonely abyss of interstellar space. Our solar system, it seemed, was not the blueprint, but perhaps just a lucky survivor, a place where the giants knew their place and stayed put. This revelation was as profound as it was terrifying. The universe was not a serene and predictable clockwork machine. It was a far more dynamic, violent, and unpredictable place than we had ever dared to imagine. The discovery of hot Jupiters opened the floodgates, but the radial velocity method, for all its power, left us with a frustratingly incomplete picture. It gave us a planet's minimum mass and its orbital period, but it told us nothing about its physical size. We were detecting the dancer's pull, but could not see their silhouette. A new technique was needed to bring these phantoms into the light, and it came in the form of a method as simple in concept as it is difficult in practice, the transit. The idea is wonderfully straightforward. If a planet's orbit happens to be aligned perfectly edge-on from our perspective here on Earth, then once per orbit it will pass directly in front of its star, casting a shadow in our direction. For a few precious hours it will cause a tiny, almost infinitesimal dip in the star's brightness. It is a celestial blink, a cosmic moth, momentarily flitting across a distant torch. The challenge is one of scale and precision. A Jupiter-sized planet crossing a sun-like star blocks only about 1% of the light. For an Earth-sized planet, that drops to less than 1/100%. Detecting such an ephemeral dip requires photometers of incredible stability, monitoring thousands of stars, continuously searching for that one faint periodic wink that betrays the presence of a hidden world. The first confirmed transit of an exoplanet in 1999, a hot Jupiter named HD 29458b, was a watershed moment. It was the crucial piece of the puzzle. Suddenly we could see the planet's shadow, and from the depth of that shadow, how much the starlight dimmed, we could calculate its physical radius. We finally knew how big these worlds were. And when astronomers combined the size from the transit with the mass from the radial velocity wobble, they could do something truly remarkable. They could calculate the planet's density. This was the moment of truth. If these objects were dense, they might be some new, exotic type of giant rocky world. But the numbers confirmed our wildest suspicions. HD 29458b had a mass similar to Jupiter's, but was significantly larger, puffed up and bloated. Its density was less than that of water. It was a vast, tenuous ball of gas, so swollen by the intense heat of its star that it would float in a bathtub if you could build one large enough. The transit method proved beyond any doubt that the hot Jupiters were real, and they were even stranger than we had imagined. They were a new class of celestial object worlds of impossible scale and temperature, existing on the razor's edge between a planet and a star. The age of exoplanet speculation was over, and the era of exoplanet characterization had begun. With their mass and size finally pinned down, we were no longer just chasing shadows. We could begin to ask the next most tantalizing question of all: what are these worlds actually like? The physics of a hot Jupiter environment is a study in extremes, a realm so far removed from our own experience that it borders on the fantastical. Imagine a world forever locked in a gravitational embrace, with its star one hemisphere trapped in perpetual blistering daylight, the other in an eternal frozen night. On the dayside, temperatures could soar to thousands of degrees hot enough to melt lead, then steel, then rock itself. The atmosphere, superheated from above, would expand and boil into space, a constant stream of gas bleeding away from the planet like steam from a kettle. This immense temperature difference between the searing day and the frigid night would create a pressure gradient of unimaginable force-driving winds that would make any hurricane on Earth seem like a gentle breeze. We theorized about supersonic jet streams thousands of miles per hour, perpetually circling the globe, carrying the infernal heat from the dayside around to the dark. These were not just planets. They were colossal heat engines, furnaces of a size and fury that dwarfed anything in our own solar system. and within these atmospheric cauldrons, chemistry itself would be transformed into something utterly alien. On Earth, we think of clouds as being made of water ice or liquid droplets. But in a place where the air itself is hotter than a blast furnace, what could possibly condense to form clouds? Scientists began to build new models, pushing the boundaries of physics and chemistry. Perhaps they mused in the upper, slightly cooler layers of these atmospheres, exotic materials could condense. Clouds not of water, but of silicates vaporized rock, forming shimmering glassy hazes. Perhaps even more astonishingly, elements we consider the very definition of solid, the metals that form the core of our own world, could be driven into a gaseous state by the relentless stellar radiation. Iron, titanium, aluminum, could they exist as a vapour swirling in the incandescent winds? And if that vapour were to be blown around to the planet's colder night side, what would happen? Could it condense? Could it fall? The idea was almost too outlandish to voice a concept ripped from the pages of science fiction. The possibility of weather systems built not from water but from molten metal. A world where the skies might be filled with clouds of iron, and where the forecast called for a rain of liquid steel. This was the breathtaking, terrifying vision that the discovery of hot Jupiters had unleashed. It was a theoretical dream, a spectacular hypothesis, born from the first faint signals from these impossible worlds. To prove it, however, we would need more than a wobble or a wink. We would need to somehow capture the light from these alien skies themselves, a feat that would require a new eye on the cosmos, a technological marvel more powerful than anything that had come before. And so we found them. A torrent of new worlds revealed not as shining orbs in a telescope, but as fleeting rhythmic dips in the light of a distant star. Thousands of them. Rocky super-Earths, gaseous mini-Neptunes and planets so strange they defy our neat, solar system-born classifications. We had created a galactic map, but it was a map of ghosts of shadows. We knew where they were, we knew their size and their year, but of their nature, of their substance, we knew almost nothing. What does it feel like to stand on these worlds? What colour is their sky? What winds scour their surfaces? To answer these questions, we had to learn how to perform the most delicate, the most audacious act of cosmic eavesdropping ever conceived. We had to learn to read the air of a planet light years away. The challenge is almost impossible to overstate. Imagine trying to discover the scent of a single flower in a distant rainforest, not by travelling there, but by analysing the sunlight that has passed through the canopy miles above it. The signal you are looking for is almost infinitesimally small, a cosmic whisper buried in the roar of a star. The only tool we have for this impossible task is a phenomenon of elegant simplicity, the transit. As a planet journeys across the face of its parent star, from our perspective, a tiny sliver of starlight filters through its atmosphere, that tenuous, gaseous halo clinging to the world's edge. For a few precious hours, that starlight becomes a messenger. It carries a secret. Starlight, when you break it down into its constituent colours, is a rainbow, a spectrum. But when it passes through a planet's atmosphere, something changes. The atoms and molecules floating in that alien air act like tuning forks, each one resonating with and absorbing a very specific wavelength of light. Sodium atoms will steal a sliver of orange-yellow, potassium will snatch a bit of deep violet, water molecules will bite out huge chunks from the infrared. When that light finally reaches our telescopes on Earth, it arrives with pieces missing. The perfect stellar rainbow is now crosshatched with fine dark lines, a celestial barcode. This is a planet's atmospheric fingerprint. By reading that code, by seeing which colours are absent, we can deduce what elements are present. We can in essence touch the sky of a world we can never visit. For decades, this technique of transit spectroscopy remained our best hope, our only hope for understanding these newfound worlds, and we had titans in the sky to help us. The Hubble Space Telescope, our faithful eye in orbit for over 30 years, gave us our first tantalising glimpses. It could see the barcode. Hubble was the pioneer, confirming the presence of simple elements like sodium and potassium in the atmospheres of the largest, most inflated hot Jupiters. It even found the first hints of water vapour, the chemical signature we so desperately search for. But Hubble, for all its power, was an instrument built for a different era, designed primarily to see the universe in visible and ultraviolet light. Many of the most revealing fingerprints, the complex signatures of molecules that tell the true story of a world's climate and composition, are hidden deeper in the spectrum in the infrared realm of heat. Hubble was reading the book of exoplanets, but it could only see every other page. To peer into that invisible world of heat, we had another champion, the Spitzer Space Telescope. Spitzer was an infrared specialist sensitive to the warm glow of the cosmos. It could sense the broad strokes of an atmosphere's chemistry, detecting the chunky absorption bands of water and carbon monoxide. It told us that these hot Jupiters were not simple uniform spheres, but complex worlds, with weather, with clouds, with chemistry. Yet Spitzer also had its limitations. Its mirror was small, its vision less sharp than Hubble's. It could hear the orchestra of an alien atmosphere, but only the loudest instruments. It could detect the booming trombones of water vapour, the blaring trumpets of methane. But the subtle, quieter notes, the whisper of a flute, the pluck of a harp, were lost in the background noise. The data was often smeared the barcode blurry, leaving us with more questions than answers. And so we found ourselves in a state of exquisite frustration. With Hubble and Spitzer working in concert, we began to probe the most extreme worlds we had yet discovered, the ultra-hot Jupiters. These are gas giants on suicidal orbits, whipping around their stars in a matter of days, sometimes even hours. They are blasted with radiation thousands of times more intense than that which strikes our own Jupiter. On these worlds, we began to see hints of something truly bizarre. The data was noisy right at the edge of detection, but the barcode seemed to be telling us an unbelievable story. We saw suggestions of titanium oxide, the same stuff used to make white paint. We saw whispers of vanadium oxide. These weren't just simple gases anymore. These were vaporized metals, the components of rock itself, floating as a gas in the planet's sky. But were these detections real? Or were they phantoms in the data ghosts created by the thrum of the telescope, the mottling of the star's own surface, or our own eagerness to find the exotic? Every tantalizing signal was shrouded in uncertainty. We were like archaeologists who had found a single indecipherable hieroglyph, knowing it was part of a grander story but lacking the Rosetta Stone to translate it. The evidence was compelling, but never conclusive. We were standing on the shore of a vast new ocean of knowledge, able to see the shimmer of strange leviathans beneath the surface, but unable to bring a single one into the clear light of day. To go further to confirm these phantasmal signals, we needed a world so extreme, so perfectly positioned, that its atmospheric secrets would be written not in whispers, but in a roar. We needed a natural laboratory forged in the crucible of a star. And then we found it. 640 light-years from Earth in the constellation of Pegasus, there is a star. Slightly larger and significantly hotter than our Sun, it burns with a fierce white-hot intensity. And around this star, something monstrous is turning. A planet designated WASP-76b. It is a Goliath, a gas giant nearly twice the width of our own Jupiter, yet it possesses slightly less mass, making it a puffy, incredibly inflated beast. But its size is not what makes it so utterly compelling. It's the planet's proximity to its star. WASP-76b orbits in a breathtaking frenzy. Its year, the time it takes to make one full circuit, is not 365 days. It is 1.8 days. It skims its sun at a distance more than 10 times closer than Mercury is to our own, locked in a gravitational embrace of terrifying intimacy. This proximity has forged the planet into something unimaginable. Like our moon is to the Earth, WASP-76b is tidally locked to its star. The immense gravity of its parent sun has arrested its rotation, clamping it into a fixed orientation. This gravitational shackle means that one side of the planet, the dayside, is condemned to perpetually face the stellar furnace. It never sees a sunset. It never knows a moment's respite. It is locked in an eternal, unending noon. The other side, the night side, faces the opposite fate. It is forever turned away, staring out into the freezing, empty void of interstellar space. It never sees a sunrise. It exists in a permanent, unending midnight. This stark division, this planetary duality, is the key that would unlock a weather system from a fever dream. Let us for a moment step into the realm of theory. Based on the star's heat and the planet's orbit, astronomers could build a model, a prediction of what this world must be like, and the physics painted a portrait of hell. On the dayside, under the relentless unblinking glare of its star, the temperatures would defy comprehension. The models predicted that the upper atmosphere would soar past 2,400 degrees Celsius. That's over 4,400 degrees Fahrenheit. Hot enough to vaporize lead, copper, aluminum, titanium, hot enough to vaporize iron. At these temperatures, chemistry as we know it ceases to exist. The bonds that hold molecules together are ripped apart by the sheer thermal violence. Water is shredded into its constituent hydrogen and oxygen atoms. Carbon dioxide is sundered, and the very rock-forming elements that make up the planet's core and mantle, silicates and metals, could no longer remain solid or even liquid. They would be boiled away, turning into a vapor, a gas of incandescent rock that would puff up the atmosphere, making it a vast searing envelope of atomized minerals. Imagine floating in that sky. You would not see clouds of water ice as we do on Earth. You would be surrounded by a transparent shimmering haze of gaseous iron, the very substance of steel, not as a solid, but as a breathable component of the air every bit as common as nitrogen is in our own atmosphere. This was the prediction, a world whose permanent dayside was a blacksmith's forge the size of a planet, constantly turning solid metal into a metallic vapor. But that is only half of the story. The other half plays out on the far side of the world in the eternal dark. Here, shielded from the direct stellar blast, the temperature plummets. It's no winter paradise. The model still predicted a searing 1,500 degrees Celsius. But that drop of nearly 1,000 degrees from day to night is the most extreme temperature differential ever contemplated on a planet. And in atmospheric physics, a temperature difference is a recipe for wind. Not just a breeze, not a gale, but a perpetual planet-circling hurricane of almost unimaginable ferocity. The superheated gas on the dayside, expanding and rising, would create a colossal pressure gradient, driving winds that scream from the light into the dark. A jet stream moving at thousands of kilometers per hour, a river of superheated plasma constantly flowing from the point of highest heat across the boundary that separates day from night. This boundary, the terminator, is a zone of perpetual twilight, a permanent sunset on one side of the planet and a permanent sunrise on the other. And it is here in this twilight zone that the true spectacle was predicted to unfold. The entire theoretical framework, all the physics of heat and motion, led to one spectacular, almost unbelievable hypothesis. As that ferocious wind carries the atmosphere of the dayside over the terminator and into the relative cool of the night side, the cargo it carries, that transparent shimmering vapor of iron, would suddenly find itself in a changed environment. The temperature drops below iron's condensation point. Just as water vapor in Earth's atmosphere cools and condenses into liquid water droplets to form clouds, the iron gas on WASP 76b would cool and condense. It would transform from an invisible gas into microscopic droplets of liquid metal. An iron fog would form. Clouds of molten iron would billow in the twilight sky. And as these droplets grew heavier, coalescing in the turbulent atmosphere, they would begin to fall. It would begin to rain. A downpour not of water but of shimmering molten iron, cascading through the perpetual darkness of the night side, falling towards a planetary interior we can only imagine. This was the extraordinary, audacious theory. A world of two faces, one that melts iron and another where it rains from the sky. It was a vision born from the cold, hard logic of physics, but it sounded like something torn from the pages of ancient mythology. The problem was, it was only a model. A ghost story told in equations. To prove it, to truly know if this metal rain was real, we would have to catch the planet in the act. We would need to find the chemical fingerprint of that iron gas shining brightly on the dayside as the planet began its transit, and then watch it vanish as the twilight terminator, the zone of iron rain, rotated into our view. The signal would be subtle, an ephemeral change in a barcode of light from 640 light-years away. Our old telescopes, for all their glory, were not enough. The symphony was too complex, the notes too fine. To hear this impossible music, we would need a new maestro. We would need a new eye on the sky, one with the power to finally turn this cosmic ghost story into an observed reality. And so, for years, the tantalizing evidence remained just that. A ghost in the machine, a whisper in the data. Humanity's most powerful ground-based observatories, giants of glass and steel had strained to their absolute limits, peering across 640 light-years of unforgiving space. They had captured a fleeting shadow, a subtle dimming of starlight that hinted at a world of unimaginable extremes, a planet where clouds of iron condensed and rained into a boiling abyss. The theory was as elegant as it was terrifying, a perfect and horrifying consequence of a planet locked in a gravitational death spiral with its star. Yet the proof remained stubbornly incomplete, obscured by the very thing that protects us, our own atmosphere. Earth's turbulent blanket of air, the life-giving shield for our world, is a constant shimmering veil for astronomers. It blurs it, distorts it, absorbs the very wavelengths of light that carry the most intimate secrets of these distant worlds. Water vapour in our own skies, for instance, mimics the signature of water on an exoplanet, creating a confounding echo in the data, a source of perpetual uncertainty. Scientists could model, they could infer, they could argue with passionate conviction, but they could not definitively know. They were like detectives trying to solve a murder by examining a single smudged fingerprint found at the bottom of a murky lake. The core of the mystery, the unambiguous chemical signature of neutral iron atoms condensing on one side of the planet and vanishing on the other, was a truth hovering just beyond our grasp. A new kind of eye was needed, an eye that could leave the shimmering haze of Earth's cradle behind entirely, one that could stare cold and unflinching into the deep infrared, the hidden spectrum where the chemical stories of atmospheres are written in blazing light. For decades, it was a dream, an engineer's fantasy sketched on blueprints, a multi-billion-dollar gamble on the very edge of technological possibility. Then, on a Christmas morning that felt like the dawn of a new era, that dream ignited into a pillar of controlled fire. Rising from the jungles of French Guiana, the James Webb Space Telescope began its journey not just into space but into time. This was no mere successor to Hubble. It was a fundamentally different kind of being. Hubble gave us the grand portrait of the cosmos in visible light, the universe as our eyes might see it. But Webb was designed to perceive a different reality altogether. Its gaze is tuned to the infrared, the realm of heat and birth, the light emitted by the coolest, most distant and most obscured objects in existence. To achieve this, it had to become one of the coldest things humanity has ever built. Its destination was not a simple orbit around the Earth, but a lonely gravitationally stable point 1 million miles away known as L2. Here, shielded from the blinding glare of the Sun, the Earth and even the Moon by a 5-layered sun shield the size of a tennis court, the telescope could cool down to a staggering 230 degrees below 0 Celsius. The journey itself was a ballet of unprecedented complexity, a month-long multi-stage deployment where thousands of individual parts had to work in perfect sequence with no possibility of a repair mission. Motors, latches, cables and tensioners all performing a silent automated choreography that held the breath of the entire scientific world. And at its heart, the centerpiece of this technological miracle, the mirror, an immense honeycombed marvel of beryllium-18 hexagonal segments polished to near atomic perfection and coated in a microscopically thin layer of pure gold. Gold not for its beauty, but for its superlative ability to reflect infrared light. This golden eye, spanning over 6.5 meters, was a light bucket of immense power, capable of gathering photons that had been traveling across the universe for over 13 billion years. But for the researchers studying WASP-76b, its power wasn't just about seeing farther back in time. It was about seeing with an entirely new kind of clarity. It was about transforming the science of exoplanet atmospheres from a discipline of educated guesswork into one of exquisite precision. The technique it would employ is called transmission spectroscopy, a method of breathtaking elegance. For a brief period during the planet's orbit as it passes in front of its star from our perspective, a tiny fraction of the starlight filters through its atmosphere. This is the moment of truth. As that light streams through the tenuous envelope of gas, the different atoms and molecules within the planet's sky each absorb very specific frequencies, very specific colours of light. Imagine the star's light as a perfect, complete rainbow. After passing through the atmosphere of WASP-76b, that rainbow emerges on the other side, but now it is scarred. It is missing tiny razor-thin slivers of colour. These missing slivers create a pattern of dark lines, a celestial barcode, and this barcode is a definitive, unmistakable fingerprint. Every element, every molecule has its own unique spectral signature, its own pattern of absorption lines that it alone can produce. Sodium has one pattern, methane another, water vapour a third. And neutral iron, the suspect at the heart of our mystery, has its own very particular, very complex signature. Ground-based telescopes could see the blurry outline of this barcode, the equivalent of a few thick smudged lines. They could say with some confidence that iron was present in the atmosphere, a monumental discovery in itself. But Webb could do something that was previously unthinkable. With its incredible stability, its frigid operating temperature and its powerful spectrographs, it could resolve that blurry smudge into a high-definition image. It could see not just a few lines, but a forest of them. It could read the entire barcode with every fine detail intact. This meant scientists could move beyond simply detecting an element. They could now measure its abundance with stunning accuracy. They could map its distribution, seeing how its concentration changes with altitude and temperature. And most critically for WASP-76b, they could watch in near real time how that fingerprint changed as the planet rotated. The mission plan was as audacious as the telescope itself. Webb would not just take a single snapshot. It would stare unblinking at the WASP-76 system for the entire duration of the planet's transit, a precious window of just a few hours. As the planet first began to cross the face of its star, Webb's instruments would capture the light filtering through the atmosphere at the morning terminator, the edge leading into the planet's dayside inferno. This was the region where temperatures soar to over 2400 degrees Celsius, hot enough to vaporize not just iron, but rock itself. Here, if the theory held true, the spectral barcode should scream with the presence of gaseous iron. The absorption lines for iron should be deep and clear, a dominant feature of the atmospheric chemistry. It would be the chemical signature of a sky filled with metal vapor. But the crucial test would come hours later. As the planet continued its swift journey across the star's face, Webb would remain locked on now, capturing the light filtering through the evening terminator, the boundary rolling into the planet's perpetual night. This is the line of condensation, the cosmic waterfall of shadow. Here, as the atmosphere is whipped around the planet by ferocious winds into the cooler night side, the vaporized iron should in theory begin to cool and condense. It would transform from a gas into microscopic liquid droplets. It would form clouds, and once it becomes a liquid, it no longer absorbs light in the same way. The clear, sharp, spectral fingerprint of gaseous iron should vanish. It shouldn't just fade. It should disappear completely from the data. The barcode should be wiped clean of its most prominent feature. Finding iron vapor on the morning side would be a confirmation of previous work. But seeing it disappear on the evening side, that would be the smoking gun. That would be the closest thing to watching the iron rain actually begin to fall, an observation made across the gulf of 6 trillion kilometers. It was a hypothesis of sublime and terrible beauty, and the moment had finally come to test it. The observation was scheduled. The commands were coded. Across the unimaginable distance, the James Webb Space Telescope, humanity's golden eye, in the dark received its instructions. Slowly, silently, its gyroscopes whirred, slewing the massive structure through the void. The light from a star named WASP-76, a star much like our own sun but for its captive monster, began its final journey. After travelling for 640 years, that ancient starlight carrying the ephemeral chemical story of an alien world's edge bounced off the shimmering gold hexagons of the primary mirror. It was focused with unparalleled precision onto a smaller secondary mirror and then beamed deep into the heart of the observatory, into the waiting maw of the near-infrared spectrograph or NER spec. Inside this instrument, cooled to a temperature that borders on absolute zero, the light was meticulously broken apart. Prisms and gratings split the singular beam into its constituent wavelengths, spreading it out like a fan into its full glorious spectrum. Every photon was a messenger, every wavelength a piece of the puzzle. The faint stream of infrared light, a whisper from a hell world, was projected onto a detector array of hypersensitive mercury-cadmium telluride pixels. For hours, the telescope gathered this fragile information, building up the signal photon by precious photon. It was watching the planet's shadow dance across its star, tasting the chemical makeup of its atmosphere at the beginning and the end of its brutal day. On Earth, in control rooms and university offices, the scientists could only wait. They had spent their entire careers building towards this moment, dreaming of a telescope with the power to answer these very questions. They had debated the physics, run the simulations, and defended the theory. Now the truth was being collected. The raw data, the pure unanalyzed stream of ones and zeros, began its 15-second journey back across the million-mile gap to Earth, received by the giant antennas of the Deep Space Network. Contained within that digital flood was the answer. Not an inference, not a model, but a direct observation. A definitive spectrum, a chemical map of the line between eternal day and eternal night. The barcode from the edge of damnation had arrived, and now the painstaking work of decoding its message was about to begin. The question that had haunted them for years lingered in the silent tension of the control room. What secrets were written in that light? What would the golden eye reveal about the world where the sky rains iron? And so the floodgates opened, not with the roar of water, but with the silent, insistent whisper of photons journeying for 50 quadrillion kilometers, their long pilgrimage finally ending on the gilded mirrors of the James Webb Space Telescope. From the Lagrange point, 1.5 million kilometers from Earth, the data began its final radiant descent, a waterfall of light, a river of numbers cascading into the servers and data centers of the Space Telescope Science Institute. This was not a simple picture, not a single snapshot to be admired. It was a deluge, an overwhelming torrent of information representing every subtle shift in starlight, as WASP 76b, a world of fire and shadow, danced before its parent star. Each packet of data was a coded message from the edge of twilight, a ghost of a whisper from an atmosphere under unimaginable duress. The raw files were colossal, intricate, and to the untrained eye utterly chaotic, a blizzard of digital noise. Yet buried within that storm of information like a single perfect fossil, preserved in ancient stone, lay the secret we had sent our greatest technological eye to find. The hunt had truly begun. For the international teams of astronomers and astrophysicists, this moment was the culmination of years of planning, of proposals, written and defended, of simulations run and rerun. The air in their labs was thick with a unique blend of exhaustion and electric anticipation. They were no longer just theorists, they were cosmic detectives, and the crime scene was a planet so hostile it defied terrestrial imagination. Their first and most crucial tool was not a magnifying glass, but a principle of physics, as fundamental as gravity itself, spectroscopy. It is the art of dissection, the science of performing an autopsy on starlight. When the light from the host star WASP 76 streamed through the thin, searing hot sliver of the planet's atmosphere, during its transit, the atoms and molecules swirling within that atmosphere acted like billions of tiny selective filters. Each element, each molecule, possesses a unique energy signature, a set of specific frequencies of light. It is programmed by quantum mechanics to absorb. As the white light of the star passed through this atmospheric gauntlet, certain colours, certain precise wavelengths were plucked out, stolen by the atoms, and never completed their journey to us. What arrived at JLST's instruments was a wounded rainbow, a spectrum of light riddled with impossibly fine dark lines. These are absorption lines, and they are nothing less than the chemical fingerprints of an alien sky. This is not a simple process of just looking at a pretty rainbow. The NIRSpec instrument, Webb's near-infrared spectrograph, is a marvel of precision, capable of splitting the incoming light into over 250,000 individual shades of colour. Imagine a piano, not with 88 keys, but with 250,000, each one representing a unique sliver of the electromagnetic spectrum. The scientists were listening for a missing note, a silent key in a cosmic symphony. To find the signature of iron, they needed to know its song. In a laboratory on Earth, when you heat iron until it vaporizes, it casts a very specific and complex shadow on any light that passes through it. Not a single dark line, but a dense forest of them, a unique and unmistakable pattern. This pattern, this cosmic barcode, was what the teams were hunting for. They fed this known fingerprint into their sophisticated computer algorithms and set them loose upon the mountains of data from Webb. The software began its work sifting, comparing, cross-referencing terabytes of information, tirelessly searching for a match between the known signature of iron vapor and the shadows found in the light from WASP 76b. Days turned into a week. The initial data runs were promising but inconclusive, the signals buried deep within the instrumental noise and the inherent flicker of the host star. This is the painstaking reality of modern astronomy. Long periods of intense meticulous work, punctuated by moments of sheer heart-stopping revelation. The teams had to carefully model the star's own light, subtracting it from the equation to isolate the planetary signal, a process akin to trying to hear a single person's whisper in the middle of a roaring stadium. They filtered out the gravitational wobbles of the telescope itself, the thermal emissions from its own instruments, and the faint intervening signatures from interstellar dust clouds the light had passed through on its epic journey. They were peeling back the layers of the universe one by one to isolate a single fragile signal from a world we can never touch. It was an act of supreme technical fidelity, pushing the very limits of what we know how to measure. And then it happened. Not with a sudden crash, but as a pattern slowly resolving from the noise becoming clearer and more defined with each successive processing run. It was undeniable. There, imprinted on the light that had grazed the planet's blistering dayside, was the forest. The dark, intricate and perfectly matched absorption lines of gaseous, vaporized iron. It was a chemical scream from a world trapped in a star's inferno. The data was unequivocal. On the hemisphere of WASP 76b, that is forever locked facing its sun, where temperatures soar to a mind-bending 2,400 degrees Celsius, the atmosphere is saturated with iron gas. You must pause and comprehend what this truly means. This is not the solid, familiar metal of our buildings and our blood. This is iron behaving like water vapor on a hot summer's day on Earth. The sheer thermal violence of the dayside is so extreme that it rips metal apart atom by atom and boils it into a transparent, shimmering gas. The planet's sky is in a very real sense made of metal. We were seeing the direct proof of a celestial blacksmith's forge, a place where the distinction between rock metal and air simply ceases to exist. The energy pouring onto this face of the planet is so relentless, so overwhelmingly powerful, that it sustains an atmosphere of what should be a solid. It was a discovery that confirmed our most extreme models, a finding that was both terrifying and profoundly validating. But this was only half of the story. The true mystery was about to unfold. Every planet that is tidally locked has a terminator, that permanent razor-thin line that separates eternal day from unending night. As WASP 76b continued its orbit, the slice of atmosphere that Webb could see shifted. The telescope began to analyze the light passing through the atmosphere just past the terminator at the very edge of the night side. The teams watched their screens, expecting to see the iron signature perhaps weaken as the temperatures began to drop. They expected a gentle transition, a gradual fading of the signal. What they saw instead was a stunning, abrupt and profound silence. The iron was gone, completely. The dense forest of absorption lines that had been so clear and bold on the dayside had utterly vanished from the spectrum. It was as if a cosmic switch had been flipped. On one side of the planet, a sky of boiling metal. On the other, just meters across the terminator line into the shadows, nothing. The iron fingerprint was wiped clean. The initial reaction in the science labs was one of disbelief, followed by a frantic search for error. Could the instrument have failed? Was there a flaw in the data processing for this phase of the orbit? They ran every diagnostic imaginable. They recalibrated their models. They triple-checked every line of code. But the result held firm. The data was pristine. The absence of the signal was as real and as significant as its presence had been moments before. This wasn't an error. It was a clue. A colossal planet-sized clue that pointed to a dynamic of unimaginable scale and violence. Why would an element so abundant on one side of a world be completely missing on the other? The night side of WASP 76b, while still incredibly hot by any earthly standard, is significantly cooler than the dayside, plunging to around 1500 degrees Celsius. This is still hot enough to melt lead, but it represents a thermal gradient, a temperature difference of nearly 1,000 degrees across the planet. This staggering differential is the key to the entire puzzle. Nature abhors a vacuum, but it despises an imbalance even more. A 1,000-degree difference between two adjacent regions of a gaseous atmosphere creates a pressure differential of titanic proportions. It is the perfect recipe for wind. Not a gentle breeze, not even a terrestrial hurricane, but a permanent planet-girdling tempest, driven by the raw thermal power of a nearby star. The scientists began to realize they were not looking at two separate static atmospheres. They were witnessing a single gargantuan atmospheric system in motion. The iron vapor boiled into existence in the crucible of the dayside doesn't simply stay there. It is caught in this monumental atmospheric flow, a conveyor belt of superheated gas moving at incredible speeds. The data was pointing to a wind, a jet stream of vaporized metal being relentlessly driven from the blistering heat of the dayside into the relative cool of the eternal night. This atmospheric river, carrying its impossible cargo of gaseous iron, flows across the terminator into a region where the temperature is no longer high enough to keep it in its vaporous state. Here in the perpetual twilight and encroaching darkness of the night side, the iron gas is subjected to a rapid and dramatic cooldown. And just as water vapor in Earth's atmosphere cools and condenses to form clouds and rain, the iron vapor on WASP-76b must undergo a similar transformation. It has reached its cosmic dew point. The laws of physics are absolute and unforgiving. The iron cannot remain a gas in these cooler temperatures. It must change its state. It must condense. This is why the spectral signature vanishes so abruptly. The moment the iron gas crosses into the night, it is no longer a gas. The atoms are no longer floating individually capable of absorbing starlight in their characteristic way. They are instead clumping together, cooling and coalescing out of the atmosphere. The shadow they once cast on the starlight is gone because the iron itself is transforming into something else entirely. The empty spectrum of the night side was not telling us what wasn't there. It was screaming to us about a process that was actively happening. It was the definitive evidence of condensation on a planetary scale. We had not only found the ingredients for a storm, we had found the engine that drives it, and the cold front that triggers it. We had pieced together the entire weather system. The only question that remained, the one that hung in the air with terrifying and beautiful weight, was what form does condensing iron take? When metal cools from a gas, what does it become? We had followed the evidence to the edge of the abyss, and it was pointing to one inescapable and truly spectacular conclusion. It was pointing to rain. And so, the pieces were on the board. From the unblinking eye of the Webb telescope, we had received a ghost story, written in the language of light, a spectral tale of two worlds occupying a single sphere. On the western limb, as WASP-76b emerged from behind its star, the chemical signature of iron was unmistakable, a bold, clear declaration etched into the starlight filtering through its upper atmosphere. But on the eastern limb, as the planet prepared to pass back into the glare, that same signature had vanished. Iron was present, and then it was gone. An element fundamental to our own world, a substance we perceive as the very definition of solid, was behaving like a phantom, a fleeting atmospheric vapor. The data was not a suggestion, it was a cosmic dare. It challenged us to reconcile two seemingly impossible truths to explain an atmospheric disappearing act on a scale that beggars belief. For the teams of scientists who had spent years preparing for this very moment, this was not a contradiction, but a confirmation, the final crucial clue in a puzzle of unimaginable proportions. The moment had arrived to move beyond theory, beyond inference, and to build a working, breathing model of this infernal world, a digital twin forged from physics, and validated by Webb's impeccable observations. It was time to construct piece by agonizing piece the grand unified cycle of WASP-76b's weather. Building a world from scratch, even a digital one, is an act of supreme ambition. It begins not with clouds or winds, but with the cold, hard mathematics that govern all matter in the universe. Supercomputers humming in climate-controlled rooms were tasked with this colossal undertaking. They began by ingesting the fundamental parameters of the system, the mass of the planet, its radius, its gravitational pull, the searing, relentless energy pouring from its parent star. These were the unchangeable laws of this alien kingdom. Upon this foundation, the modelers began to layer the complexities of an atmosphere, a task akin to teaching a machine to dream. They programmed the laws of fluid dynamics, the same principles that describe the flow of water from a tap or the swirl of cream in coffee, but supercharged them for a far more violent and exotic medium. They had to account for an atmosphere composed primarily of hydrogen and helium, superheated to thousands of degrees, behaving in ways that defy our terrestrial intuition. These gases under such extreme temperatures are not gentle breezes. They are a seething, roiling fluid, a planetary ocean of incandescent air. The equations had to predict how this fluid would respond to the most extreme temperature gradient imaginable in our cosmic neighbourhood. A dayside permanently locked in a star's unforgiving gaze and a nightside perpetually cast in shadow, creating a thermal differential so vast it becomes the primary engine of the planet's entire climate system. Into this digital crucible they introduced the crucial element iron, not as a solid, not as a liquid, but as a gas. They had to calculate its unique properties at every conceivable temperature and pressure, from its boiling point of nearly 3,000 degrees Celsius all the way up to the point where its atoms are stripped of their electrons, becoming an ionized plasma in the planet's upper reaches. They created what is known as a radiative transfer model, a complex simulation that calculates how starlight penetrates this strange atmosphere, how it is absorbed by different elements, and how that absorbed energy as heat drives the planet's circulation. Every atom of iron gas was a tiny variable, a microscopic sponge for starlight, and the collective effect of trillions upon trillions of these atoms would determine the fate of the world's weather. The initial models were chaotic digital storms of incomprehensible data. Some simulations collapsed, unable to handle the sheer extremity of the conditions. Others produced weather systems that were physically nonsensical, failing to match the tantalizing clues provided by earlier telescopes and now by Webb. The scientists refined their assumptions, tweaked the variables. What was the true abundance of iron? How much silicate dust might be present acting as seeds for condensation? Slowly, painstakingly, through countless iterations and immense computational effort, a coherent picture began to emerge. The digital storm began to resolve itself into a stable, predictable, and utterly terrifying pattern, a model that didn't just suggest a strange weather phenomenon but demanded it. And when they finally ran Webb's precise spectral data through this newly forged simulation, the results were breathtaking. The model didn't just match the observations, it explained them perfectly. The ghost in the machine had been found. Here then is the story the data tells, the full, breathtaking life cycle of iron on a world where the sky itself is a blast furnace. It all begins on the dayside, a hemisphere forever condemned to face the wrath of its sun, WASP 76. This is not a gentle, life-giving warmth. It is a torrent of radiation, a celestial blowtorch of unimaginable power, heating the atmosphere to over 4,000 degrees Celsius. At this titanic temperature, the very concept of rock and metal dissolves. The planet's surface, if one could even call it that, is a roiling ocean of magma, but the true spectacle is what happens above it. Any iron present, whether dredged up from the planet's interior or part of its primordial composition, cannot remain solid. It cannot even remain liquid. It is vaporized instantly. Imagine standing on a surface where the air itself is hotter than a steel mill. The iron atoms are torn from their bonds, energized by the stellar glare, and flung into the atmosphere. They cease to be a tangible metal and become a transparent superheated gas, an invisible component of the air mingling with the hydrogen and helium. This isn't a slow, gentle evaporation like water from a puddle on a summer's day. This is a violent, continuous sublimation, a planet's crust being boiled away into its own sky. The dayside of WASP 76b is a forge, but one that doesn't create. It dissolves. It transforms one of the strongest materials we know into a diffuse shimmering vapour, creating a vast reservoir of gaseous iron that saturates the upper atmosphere. This is the source, the great furnace that perpetually feeds the planet's unholy meteorological engine. And as this reservoir of vaporized metal builds, it is caught by the single most powerful force on the planet, the wind. The sheer temperature difference between the dayside and the nightside creates a pressure gradient of astonishing force. The superheated, expanded atmosphere on the dayside is in a constant state of explosive pressure, while the cooler, denser air on the night side creates a vacuum. Nature, as it always does, abhors this imbalance, and its solution is wind. But these are not the winds of Earth. They are not gales or hurricanes. They are a singular planetary-scale atmospheric conveyor belt, a jet stream of fire and metal moving at speeds that are difficult to comprehend. Our models, now confirmed by Webb's data on atmospheric movement, show these winds screaming across the planet at over 18,000 kilometers per hour. That is 5 kilometers every single second. Faster than any jet fighter, faster than the speed of sound on Earth, these winds are a relentless horizontal river carrying the superheated air and its cargo of vaporized iron away from the dayside's inferno. This is the great atmospheric river of WASP 76b, a planet-girdling current driven by the thermal engine of its star. It gathers the incandescent iron vapor from the dayside forge and begins a cataclysmic journey toward the darkness. This is not a gentle migration. It is a violent, turbulent transport, a maelstrom of superheated gas moving with such momentum that it shapes the very climate of the globe. For thousands of kilometers, this invisible stream of metal flows eastward, a constant, unending transfer of mass and energy from one hemisphere to the other. It is this incredible velocity that Webb was able to indirectly measure, detecting the Doppler shift in the iron's spectral lines, confirming that this material was indeed moving away from us at incredible speed as it approached the edge of the planet. And it is this river that carries our phantom element toward the most dramatic location on the entire world, the Terminator. The Terminator is the line that separates day from night, a zone of perpetual twilight moving across a planet's surface as it rotates. But on a tidally locked world like WASP 76b, the Terminator is not a moving line. It is a permanent fixed geographical feature, a stark, unmoving border between two utterly different realms of existence. On one side lies the blistering 4,000-degree forge of eternal day. On the other, the deep, unending darkness of the night side. Crossing this boundary is not a gradual transition, it is an atmospheric cliff, a thermal shock front of epic proportions. As that 5-kilometer-per-second jet stream laden with its precious cargo of iron vapor screams across this great divide, it is suddenly and violently plunged into shadow. The fire hose of stellar radiation is instantly cut off. In this moment, the temperature plummets. Not to a comfortable coolness, but from over 4,000 degrees down to around 1,500 degrees Celsius. While still fantastically hot by any earthly standard, this drop of 2,500 degrees is catastrophic for the iron vapor. It has crossed a cosmic dew point. The thermal energy that was keeping the iron atoms in their gaseous state is gone. The laws of physics now make an absolute non-negotiable demand the iron must change its state. It has no choice but to condense. What happens next is the climax of this entire atmospheric drama, the incredible event that Webb's data so powerfully predicted. In the turbulent, chaotic air just past the Terminator, the iron vapor begins to nucleate. Individual atoms, suddenly cooled, begin to clump together. Perhaps they find purchase on microscopic specks of silicate dust, using them as seeds around which to grow, much like how water vapor forms around dust particles to create raindrops on Earth. Atom by atom, molecule by molecule, the iron transforms. The transparent, invisible gas that rode the winds from the dayside spontaneously flashes into existence as a liquid. Clouds are born. But these are not clouds of fluffy white water ice. They are vast, billowing banks of molten iron droplets glowing with their own residual heat, a dull cherry red against the eternal blackness of the nightside sky. The jet stream, now carrying this impossibly heavy burden, continues its journey into the depths of the nightside. The droplets continue to grow, colliding, merging, becoming heavier and heavier. And then inevitably, gravity asserts its dominance. The clouds become too saturated, the droplets too massive for the winds to support. And the rain begins. This is the moment of final, breathtaking confirmation, the resolution of the mystery. The iron that was so clearly present as a gas on the dayside has now transformed and is falling out of the upper atmosphere. This is why Webb's instruments detected no iron vapor on the nightside's edge. It was no longer there. It was below, in a lower, denser layer of the atmosphere, falling, as a perpetual planet-wide deluge of molten metal. You have to let your imagination embrace the sheer alien majesty of this scene. A sky of black, starless hydrogen illuminated by the faint, menacing glow of clouds made of liquid iron. And from these clouds, a constant, unrelenting downpour. Not of water, but of iron droplets shimmering like tiny ball bearings at a temperature of over 1,000 degrees. A rain that would not patter but hiss and sizzle, as it fell, a shower of molten metal descending through the crushing pressure of the lower atmosphere. It falls for hundreds, perhaps thousands of kilometers, a planet-wide iron storm that rages without end. This is the proof. This is the synthesis of observation and theory. The iron disappears from the evening sky because the evening sky is raining iron. This process perfectly closes the loop on WASP-76b's weather system. The iron rains down into the deeper, hotter layers of the nightside's atmosphere, where the immense pressures and residual heat may keep it liquid or even re-vaporize it as it descends. Deeper, slower atmospheric currents, a vast and sluggish undertow beneath the high-speed jet stream, then slowly but surely drag this iron back around the planet. It completes its long dark journey, eventually re-emerging on the dayside, where it is once again blasted by starlight, vaporized and lifted back into the upper atmosphere to begin its violent 5-hour journey all over again. It is a closed, perpetual cycle of metallic weather, a planetary-scale distillation process where a world endlessly boils its own crust into the sky, transports it halfway around the globe and precipitates it back down as molten rain. We have witnessed for the first time the complete and confirmed operation of one of the most extreme weather systems in the known universe. The data from Webb was not just a snapshot. It was a feature film allowing us to see every stage of this incredible process unfold. We have stared into the heart of an alien storm and found a logic as compelling as the water cycle on our own world, yet forged in conditions of unimaginable violence. We have proven that on worlds far beyond our own the sky can fall, and it can fall as iron. The confirmation of this magnificent, terrifying cycle, however, does not mark the end of our inquiry. Instead, it flings open the door to a host of new, even more profound questions. If such a process is possible here on this one strange world, where else might it be happening? What other elements? What other bizarre forms of precipitation might be raining down on the countless other hot Jupiters we now know exist? Could there be worlds with skies of raining glass of liquid ruby and sapphire? WASP-76b is no longer just a curiosity. It is a benchmark, a Rosetta Stone for understanding the atmospheres of the most extreme planets. It has shown us that the universe is not only stranger than we imagine, it is stranger than we can imagine. And with the power of Webb, we have finally built the dictionary to translate its wonders, and so the whisper becomes a roar. The faint flickering ghost of a theory once confined to the chalkboards of astrophysicists and the complex simulations running on supercomputers is now a confirmed reality etched in the infrared light of a distant star. For years we followed the breadcrumbs, the tantalizing hints from less powerful instruments that suggested something extraordinary was happening on this distant world. We saw the subtle dimming of starlight, the ambiguous signatures that hinted at a chemical composition unlike anything in our own solar system. But hints are not proof. They are the prologue to the story, not the final chapter. The chapter we have just witnessed was written by the James Webb Space Telescope, its magnificent golden mirror collecting photons that have travelled for centuries across the sheer unforgiving void. It gathered the light that had passed through the sliver of this planet's atmosphere during its transit, a celestial alignment of impossible precision. And within that light, that impossibly faint signal, it found the undeniable, unambiguous fingerprint of iron. Not just iron as a solid element within the planet's core, but iron as a vapour, a gas swirling in a superheated sky. The final piece of the puzzle did not click into place. It slammed down with the force of a tectonic event reshaping the entire landscape of what we thought a planet could be. This moment, this definitive spectrum glowing on a screen is more than just a data point. It represents the absolute pinnacle of human curiosity, a testament to our relentless species-defining need to know what lies over the next hill, beyond the next ocean, and now across the chasm of interstellar space. Think back on the journey that brought us to this precipice of understanding. It began not with a telescope, but with an idea, a bold, almost outlandish question. Could a planet be so hot, so utterly alien, that its clouds are not of water but of rock? Could its rain be not the stuff of life but of industry? This question fueled decades of theoretical work, a painstaking construction of atmospheric models built on the laws of physics, but applied to a reality so extreme it bordered on science fiction. Then came the builders, the engineers, the thousands of brilliant minds who dedicated their lives to constructing our golden eye in the dark. We remember the breathtaking complexity of its unfolding a million-mile journey from Earth, a delicate multi-stage ballet of deployment, where a single point of failure would have meant the end of the dream. Each hexagonal mirror segment had to align with a precision measured in nanometers, a fraction of the width of a human hair, all while operating at temperatures just a few degrees above absolute zero. This magnificent instrument, the most complex and powerful observatory ever launched, is a monument to what we can achieve when we work together, when we dare to build something not for immediate profit or terrestrial gain, but for the pure, unadulterated goal of discovery. The astronomers who then received this precious data became the final link in this incredible chain. They were our digital explorers, our modern-day Magellans navigating not oceans of water, but oceans of information. They spent countless hours meticulously filtering the starlight, subtracting the signal of the parent star to isolate that whisper-thin atmospheric transmission. It was a process of extraordinary patience, a search for a single, specific shadow in a blinding ocean of light. Imagine the tension in those control rooms, the collective holding of breath as the final processed spectrum resolved on their screens. To see that deep, sharp absorption line exactly where vaporized iron was predicted to be was not just a confirmation. It was an intellectual and emotional vindication. It was the universe affirming that the strange and wonderful logic we had pieced together here on Earth also applies out there in the most extreme crucibles of creation. It was a triumph of the scientific method itself, a beautiful arc from hypothesis to observation, from a creative guess to an undeniable truth. This single discovery is the return on an investment of decades of human ingenuity, a collective effort spanning generations, proving that our reach can and often does exceed our grasp. We reached for a world of metal rain and we found it. We have touched the impossible. But what does it truly mean to find a world where it rains iron? Its significance extends far beyond being a mere cosmic curiosity, an entry in the expanding encyclopedia of bizarre planets. This discovery fundamentally recalibrates our understanding of planetary science and atmospheric chemistry. We are accustomed to our own world's gentle, life-giving water cycle: evaporation, condensation, precipitation. It is a familiar, comforting rhythm. Here we are confronted with a cycle of unimaginable violence, a geologic cycle playing out in the sky. On the planet's tidally locked dayside, a permanent furnace faces its star, roasting the surface to a temperature of 4,000 degrees Celsius. This is a heat so intense it doesn't just melt rock, it boils it. A vast atmosphere of vaporized minerals, including iron and silicates, is blasted into the sky. Supersonic winds driven by this colossal temperature gradient then scream across the planet to the permanent night side, a realm of relative cool and perpetual darkness. In this twilight zone, the vaporized iron cools and the laws of physics are absolute. It begins to condense not into delicate water crystals, but into droplets of molten metal. Picture it if you can. Clouds of incandescent iron vapor gathering in the perpetual twilight. From these metallic clouds it begins to rain. A downpour not of water, but of liquid iron glowing with its own retained heat falling through the crushing atmosphere towards a surface we can only imagine. This is not a metaphor. This is the literal physical reality on a world hundreds of light years away. This discovery forces us to discard our parochial, Earth-centric view of what an atmosphere can be made of and how it can behave. The chemical and physical processes we see here are a new frontier. How do these iron droplets interact with the other elements in the atmosphere? What kind of lightning might be generated in clouds of vaporized rock? What does this constant planetary-scale distillation of minerals do to the planet's long-term evolution and geology? These are questions we didn't even know how to ask a few years ago. The existence of this world proves that the universe is far more imaginative in its creations than we have been in our predictions. It's a cosmic menagerie filled with possibilities that stretch and sometimes shatter the boundaries of our scientific frameworks. Our models of planet formation must now expand to more readily accommodate worlds where the very ground can be lifted into the sky, transported across the globe and rained back down. We thought we were studying meteorology. We have found ourselves studying high-temperature metallurgy on a planetary scale. This discovery, as profound as it is not an endpoint. It is a gateway. It is a stunning demonstration of the James Webb Space Telescope's power, a promise of the revelations that are yet to come. If we can so clearly detect the signature of iron vapor on one world, what else are we about to find? JWST is currently turning its gaze to dozens of other exoplanets, each a unique, unexplored territory. We are on the verge of mapping the atmospheric compositions of worlds with unprecedented detail. Perhaps we will find a planet where the clouds are made not of iron, but of corundum, the mineral that forms rubies and sapphires. We might find a world so rich in carbon that its atmospheric pressure creates a rain of diamonds into a methane sea. The chemistry might be even more exotic, involving compounds and states of matter that only exist under physical conditions, so extreme we can barely replicate them in our most advanced laboratories. Each new spectrum JWST captures is a page from a book we never knew existed, telling a story of planetary diversity that is wilder and more magnificent than we ever dared to believe. And this is just the beginning of a new golden age of exploration. On the ground, a new generation of behemoths is rising. The extremely large telescope, the 30-metre telescope, the giant Magellan telescope. These colossal observatories will soon point their own massive mirrors to the sky. With a light-gathering power that dwarfs even JWST's, they will be able to dissect exoplanet atmospheres with even greater finesse. They will complement Webb's infrared vision, probing different wavelengths of light, teasing out the signatures of more subtle molecules, measuring wind speeds, and even creating rudimentary maps of cloud cover on these distant worlds. Looking further still, we are already designing the next great space observatories missions like the Habitable Worlds Observatory, explicitly conceived to find and characterize Earth-like planets around Sun-like stars. The ultimate goal of this grand endeavour is no longer a secret, nor is it a fantasy. We are searching for signs of life. The discovery of a world with metal rain profoundly impacts this search. It forces us to think more broadly, more creatively about where and how life might exist. For decades, our search has been guided by the concept of the habitable zone, the narrow orbital ring around a star where liquid water could exist on a planet's surface. But worlds like this challenge our definitions. They show us that the universe is teeming with environments that are by our standards the very definition of hell. Yet they are stable, they have complex atmospheric and chemical cycles, they exist. Could life in a form we can scarcely comprehend find a way to thrive in such places? Could there be organisms that metabolize minerals in a superheated atmosphere, or that float in the cooler layers of a gas giant's clouds? We tend to define life by its earthly manifestation, carbon-based, water-dependent. But the cosmos has shown us time and time again that our own experience is just one isolated example. The universe is not obligated to conform to our biological expectations. By studying these extreme worlds, we are not just cataloguing oddities. We are stress testing the laws of physics and chemistry, mapping the absolute limits of what is possible for a planet. And in doing so, we learn more about the true range of conditions under which life might against all odds emerge. The search for alien life may not end with the discovery of a pale blue dot, but perhaps with a signal from a world of twilight beneath a sky of molten iron. Ultimately, this journey to a world of falling metal brings us right back home. Every time we point a telescope to the stars, we are holding up a mirror to ourselves. The same ingenuity that allowed us to decode the light from a world of iron rain is the same spark that led our ancestors to control fire, to chart the seas, to unlock the secrets of the atom. We explore because it is encoded in our DNA. We look out into the great silent darkness of the cosmos, and we seek connection, context, and meaning. The discovery of a planet so profoundly different from our own serves as a powerful reminder of the preciousness and fragility of our own world. We live on a planet where the cycle of water not iron nurtures life. Our skies are gentle blue, not a searing furnace. Our clouds gift us with life-giving rain, not a metallic deluge. In the grand cosmic tapestry of worlds, with its infinite variety of violent and beautiful creations, we have found ourselves on a world of exceptional grace. And so the search continues. We will keep looking, keep questioning, keep building ever more powerful tools to peel back the layers of the cosmos, because with every new world we discover, whether it be a haven for life or a beautiful monster like the one we have just explored, we learn a little more about the universe's story, and in that story we find our own. The light from that distant iron-veiled planet will continue its journey through the universe, but for us everything has changed. We looked into the heart of a cosmic furnace and we were not blinded, we were illuminated. The night sky will never look quite the same again, for we now know it is filled not just with points of light, but with places of unimaginable wonder, with possibilities yet to be dreamed, and with the silent, patient promise of answers to questions we have only just begun to ask. The age of discovery is not over, it has just begun.